Welcome to homework.
Okay, so I don't have the full context for the experiment, but from what I can gather, there was bromobenzene. This was likely reacted with magnesium, maybe an ether, to form a Grignard reagent. Right, so that's what I can gather. Okay, and so question one is about, uh, you know, this Grignard reagent was supposed to be further reacted with some substrate, maybe, I don't know, some ketone, but that this reaction was performed in methanol, right? And so the question is, what went wrong, right? When the Grignard reagent was put into the methanol, there was a vigorous reaction, and then a volatile liquid was isolated afterwards as the main product. So, what was the reaction and what was the product? Okay, well, hopefully you recall that Grignard reagents are basically some of the strongest bases around, right? Because one way to conceptualize the Grignard reagent is not as a bond between the carbon and the magnesium there, but instead as a carbanion, right? With a magnesium bromide plus, right? So this is right there, that sort of benzene anion, phenyl anion, is, for all intents and purposes, a species in this reaction, right? And as we said, it's an incredibly strong base. So if you use any kind of protic solvent, or any kind of solvent that has OH or NH bonds, NH, N plus H, basically any acidic protons, you're going to run into issues wherein before your anion could do some sort of, attack, nucleophilic attack, it's just going to go and grab a proton, right? So what likely had happened then was that this methanol, right, reacted with the carbanion, right, yielding just benzene, right? Benzene, and then you're going to have magnesium bromide uh, associating with methoxide, right? Maybe that's a salt, but yes, this benzene is your volatile liquid, right? Benzene is the volatile liquid, and the reaction was the protonation of the phenyl carbanion. Okay, question two. A Grignard reagent was prepared by reacting bromobenzene with magnesium and diethyl ether, as we said. So we've got this species here. Carbon dioxide gas was then bubbled to the solution, resulting in the formation of a solid organic product after acidic workup. What's the structure of the solid product? Brown mechanism showing how it is formed in the reaction, right? So CO2, right? Well, what's the structure of CO2? There we are, right? That's CO2. And if you recall, if you have any kind of, let's look at an example of just acetone real quick. Recall that this carbonyl carbon is fairly electrophilic, right? Because we can draw a resonance structure for one to just kind of outline this. A resonance structure in which we get a formal positive charge on the carbon. Okay, that's a resonance structure. So it's fair to say that carbon is very electrophilic due to the double bond to oxygen, essentially. Well, that's doubly true for the carbon and carbon dioxide, because what is carbon dioxide but a carbon with two carbonyls, right? Or two double bonds to oxygen, right? So just as this nucleophilic carbon here would love to attack a carbonyl carbon on a aldehyde or ketone or ester, it's going to have no problem attacking that carbon, right? So I'm just trying to draw the mechanism here. little room. Okay. And okay, so the double bond will swing up onto the oxygen. Which we can draw as follows, right? We basically just made a carboxylate. Okay. And if we follow that up then with acidic workup, right? Acidic aqueous workup, H3O plus. Right. Then we have very clearly made benzoic acid. And we had some water left over as well. Right. What was the purpose of adding magnesium sulfate? Right. What is magnesium sulfate? Magnesium sulfate is a drying agent. Okay. I can't really draw a mechanism for it, but I will say magnesium sulfate is a white powder, and it absorbs water. Right. So it'll go from being magnesium sulfate to magnesium sulfate, some sort of hydrate, right? Some sort of number there. It might be a pentahydrate or a hexahydrate, right? But that's the point. It'll capture water molecules. Okay. And that's useful when you're working with Grignard reagents because, as we saw, any sort of OH or NH plus is going to destroy our Grignard reagent, right? Well, water, that's got an OH in it, right? So we can't have water present when we're working with Grignard reagents. So the purpose of mag sulfate is to abstract the water and prevent it from interacting with our Grignard reagents. There we are. Okay, and then the final thing we got here is that we've got cyclopentane sort of deal. Okay, and we've got two equivalents of it, and we're reacting it with an ester followed by an acidic workup. And we basically just need to show the plausible arrow pushing mechanism for the generation of the product shown. And so I'll take this opportunity to show the mechanism of Grignard acting as a nucleophile when we haven't drawn it as explicitly a carbanion with a positive magnesium bromide, but instead we'll just show this bond attacking the carbonyl carbon. Okay. Okay. And so this is commonly referred to as the tetrahedral intermediate. And typically what we find is if this is an ester, what's going to happen is that this lone pair is going to push back down to reform the double bond. And we're just going to kick off this methoxide or ethoxide as a leaving group, which isn't super common. Recall that, ethoxide's not a great leaving group, but in this case, it will be pushed forward. It's going to require some heat, but it'll happen. Okay, that will leave us with the following. Right? And as we said, we had two equivalents of our Grignard reagent. Okay, so we just repeat this process once more. Nucleophile attack on the electrophilic carbon. Okay, and then we're pretty close to the product here. All that remains is that we're going to now introduce our acid. I guess I'll draw it up here. just to protonate and form the alcohol in question. Right, and we've got our final product.